So, does anybody have one of those they want to look at? Or are you guys happy and want to talk about solving today? I will take the creepy silence as we would love to talk about solving today instead. And I'm happy for that to be the case. So, let's go ahead and do that. Okay. So, we've talked about the comparison between square roots and inverse functions quite a bit. Square roots are a nice comparison because they're a function that we're used to um, that has a similar type of restriction as our inverse trig functions do. It's nowhere near as dramatic in some ways. The idea of, oh, just ignore negatives always seems like a much clearer distinction than only consider angles within a particular range. But they both are done to accomplish the same thing, to have a one-to-one function, so our inverse is well defined. So when we evaluate this square root of 9, even though we know the square root says, what can we square to make this number, there's an inherent restriction that that response must be positive. Again, if it wasn't, then we wouldn't pass the qualifier for being a function. We have to have one and only one answer for any question. So we have decided that to make it invertible, the square root will only be defined for positive values. Similarly, when we did the sine inverse of this negative 1/2, we could only find the angle for which sine puts out a negative 1/2 that was in our restriction. So we have to only consider angles between negative pi over 2 to pi over 2 because that's where it's invertible. And if you remember graphically, that restricted us to only a piece of the sine function that looked like that from negative pi over 2 to pi over 2, where the function would go through all of its values. So every question we could ask would have an answer. And it only did it once, so that answer would be unique. So even though there are lots of angles for which sine puts out negative 1/2, 7 pi over 6 and 11 pi over 6 spring to mind, the only one that we're able to actually give is the negative pi over 6. Because negative pi over 6 on our, if we consider our unit circle, the negative pi over 6 does give us a sine value of negative 1/2, that little y value of negative 1/2, and lives within our restriction. Now, the trouble is when we go to solve, like down here when we're solving x squared equals 9, that x squared equals 9 equation, there is no square root in that equation. So that x squared equals 9 does not have the whole square roots only work on positive restriction. However, we are going to use a square root to undo that square. So we are putting in a restriction. When we put in that square root, we automatically restrict a problem that wasn't restricted before. So when we take that square root of 9 and get 3, we have to know that we restricted something that wasn't naturally restricted. So we have to undo that restriction by considering both possibilities. And you've been doing that for a long time. Most people think just like, oh, I remember when I square root, I have to take the plus or minus, and that's fine. But thinking about it as undoing the fact or fixing the fact that we're using a restricted function in an unrestricted problem is going to help us as we move towards solving trig functions. Because as we go over here to our trig function that we're trying to solve, we're going to do a similar thing. We're going to consider taking the sine inverse of both sides of this equation. And we would like the sine inverse of the sine to just be theta. And it is, as long as the answer is within our restriction. Just like the square root of x squared is equal to x if x is positive. So when we take the sine inverse over here, we are going to get that same negative pi over 6. And if we stop there, that is an answer to this question. It is a solution. Sine of negative pi over 6 is indeed 1/2. So it does count as a restriction. But we put in the sine inverse. We used a restrictive tool. So that restriction is artificial to this problem. The original problem that just said the sine of theta equals negative 1/2, that original problem didn't have any restrictions on it. So even though we're using a restrictive tool, the sine inverse, we have to undo that restriction. So we have to kind of, just like this plus or minus, we have to know that there are other possibilities for this angle. For example, not just pi over or negative pi over 6, but anything coterminal to negative pi over 6 is also going to be a solution to this problem. So we have to say negative pi over 6 can be an answer, but so could negative pi over 6 plus 2 pi. That would be 11 pi over 6. The sine of 11 pi over 6 is negative 1/2, so that would be a solution too. But not only can we add 2 pi once, we can add any multiple of 2 pi and get a coterminal. So really, if we add 1 2 pi or 2 2 pi's or 3 2 pi's, however many 2 pi's you want to add, that's going to give us something else that's coterminal. As long as that k is an integer. So as long as that k is either negative or a negative or positive whole number, any adding of 2 pi, multiple of 2 pi, is going to give us something coterminal. So again, for example, if k was equal to 1, we would get 11 pi over 6. If k was equal to 2, we'd get, would that be 23 pi over 6? If k was equal to negative 1, we'd get negative 13 pi over 6. All of those are coterminal to negative pi over 6, and all of them would give us a sine value of negative 1/2. All of them would have that same negative 1/2 y length right there, because they'd all be coterminal to that negative pi over 6. So our solution set opens up a lot more. Instead of just getting the one solution from our inverse, we get that solution and anything coterminal to that solution. And it would be nice if that was it. However, we also know that over here in quadrant 3, there's another angle. Let me try to draw it at the same. I know my circle's a little wonky. There's another angle over here in quadrant 3 where the sine value is also that negative 1/2. For example, we could use 7 pi over 6. So for example, at 7 pi over 6, we're also going to get a negative 1/2. If you look at your unit circles at 7 pi over 6, 7 pi over 6's sine value is also negative 1/2. So that 7 pi over 6 has to be another element of our solution set. But of course, if 7 pi over 6 is an element of our solution set, then so must anything coterminal to the 7 pi over 6. So 7 pi over 6 plus anything coterminal to 7 pi over 6. So instead of just the one answer, the negative pi over 6, like solving this radical, or sorry, solving this quadratic with a radical, that 3 had to be expanded to undo our restriction. It had to be expanded to plus or minus 3. Our singular answer of negative pi over 6 from the inverse has to be expanded. The difference is that expansion is much more dramatic. Instead of expanding just to a plus or minus or just to the coterminals, we have to get everything coterminal to the answer we got from the inverse, excuse me, and everything coterminal to the answer in the quadrant that our inverse didn't even know about. Before we look at a different example, I want to look at this graphically. Stop me if you have any questions. You guys are being awfully quiet and shy today. Gonna make me nervous. So if we were to graph sine normally, we've got remember our original problem was solving the sine of theta equals negative 1/2. So if we graph the sine of theta, we know the sine of theta looks like that on that side and like that on that side, where that's 2 pi, that's pi, negative 2 pi. So we know what that graph looks like. Excuse me. And we're asked to solve, where does this graph equal, sorry about the dog, where does that equal negative 1/2? Well, when we use our inverse function to do that, remember the inverse function only exists from there to there. So the inverse function naturally only gives us that answer at the negative pi over 6. We have to look at that and go, okay, I know we're going to have another answer when we go one period down, add 2 pi, and we'll get this answer as well. So that's our pi over 6 plus 2 pi. That's 11 pi over 6. We also know if we add another 2 pi, we're going to get another solution, this one. That's going to be our, 23 pi over 6. If we subtract 2 pi, we'll get another solution right there. At negative, 13 pi? No. Sorry. Negative 13 pi over 6, sorry. Negative 13 pi over 6. So we know we'll get all these extra solutions, so we have to add them in. However, notice at that graph that we're looking at, that light blue graph crosses that purple negative 1/2 more than just those coterminals to the negative pi over 6. It also crosses our graph at these points. Well, where are those points? That point is at 7 pi over 6. and everything coterminal to that 7 pi over 6. So every time we use an inverse function to solve an equation, it's going to do this. It's going to break our equation into essentially two pieces. One answer that's going to come from the inverse within our restriction. One answer that's still going to be in the first rotation, but outside of our restriction. One answer the inverse function knows about, one answer the inverse function didn't know about, and then all the coterminals on top of that. So for just this one little problem, solving the sine of theta equals -1/2, we not only get an infinite number of solutions, we get an infinite number of solutions in two groups. One group for the coterminals to -π/6, and one group for the coterminals of 7 pi over 6. Now, in case you're curious, we didn't actually have to use -7 pi over 6. We could have instead have said, wait, that is -5 pi over 6, because those are coterminal. Okay, if you'd have anchored it at -5 pi over 6, it would still work. This would still be the set of all things that are coterminal to that position, whether you anchor it at 7 pi over 6 or anchor it at -5 pi over 6 or anchor it at, oh, I don't know, what would be 19 pi over 6. Anything coterminal can be that anchor. Similarly, instead of having this be -pi over 6, we could have called that 11 pi over 6 and everything coterminal to 11 pi over 6. It's the same set because -pi over 6 is one of the coterminals. So this anchor point isn't even unique, though we do tend to make one of them the thing that comes out of the inverse function. So when we solve trig functions, because every ratio that comes out of trig functions happens infinitely many times, whenever we solve equations with trig functions in them for their angles, we're going to get essentially infinitely many answers. Let's try this again. You guys doing okay so far? You guys are really quiet, and I don't see anybody's picture, so I can't see anybody panicking. I know it's a lot, but can you guys tell me how you feel about it? Come on, folks, share your feelings with me. Any particular of the answers? Did this -pi over 6 make sense, Nick, where that came from? Okay, then let's back all the way up here. I wanted to look at another example anyway. So let's look at, we want to solve sine of theta equals, let's go with just the square root of 3 over 2. So we want to solve that. That is one of our standard ratios, square root of 3 over 2, so that'll help. So the first thing we would do, we want to solve for this theta. So we're going to go undo the sine with the sine inverse. So this side is essentially going to become theta. We've got to figure out what the sine inverse of square root of 3 over 2 is. So grab your unit circle. Hopefully you have one. Everybody grab your unit circle or a unit circle. And look at that unit circle and see where is the y value, where is the sine value, square root of 3 over 2. Now it's going to be a positive y value, so we know it's got to be in quadrants 1 or 2. So if you look at your unit circle, you'll see a positive 1/2 square root of 3 over 2 up there. And actually, you'll see another one over here at negative 1/2 square root of 3 over 2. So if this sine inverse, essentially what it's asking is, what angle makes sine output square root of 3 over 2? And within our restriction for sine, that angle should look like pi over 3. So our principal solution is going to be that pi over 3. So Nick, how about that? Is that better? Okay. Now, if it wasn't one of our nice standard ratios, we just ask the calculator what the sine inverse of the value is. We'll do one of those next. But if it's one of our standard angles, being able to work with our exact values is good. Now, as I said, this is our principal solution. It's actually a technical term. The principal solution, the principal answer is the answer that comes from the inverse function. But we know that not only is this square root of 3 going to be an answer, or sorry, not square root of 3, this pi over 3 going to give us that square root of 3 over 2 answer, but so is this other angle. It also has a y value in its intersection of the square root of 3 over 2. Now, the inverse function can only give us that pi over 3, but this angle should also work, the 2 pi over 3. And when we're solving, remember the definition of solving is finding the value or values for a variable that makes the equation true. That 2 pi over 3 will also work. So we need to have that 2 pi over 3 also as a solution. So either of those will work. So Nick, since we're talking here, does where that answer comes from make sense as well? Good. Now, it would be nice if we were done, but we also know that we're going to get that same square root of 3 over 2 answer from anything that's coterminal to that. If we add another rotation onto that, we're going to get a new angle that's coterminal to pi over 3, which is also going to have that intersection point. Furthermore, if we add 2 pi to that angle, we're going to get something else that's coterminal to 2 pi over 3 that is also going to give us the square root of 3 over 2. So to complete these answers, we have to say pi over 3 and anything coterminal to pi over 3. You kind of want to take this 2 pi k and translate it into all coterminals. The 2 pi over 3 is also a solution, but so is also anything coterminal. Again, for k and integer. The weird looking z is the notation for integer, in case you've never seen it. I'll draw it nicely. Looks like a z with a double middle bar. It's called a script z, but it's the symbol for integer. Z from the German for integer, in case you're curious. Hi, Dominic. So what about that k plus 2, or sorry, k times 2 pi, adding the coterminals? It makes sense why those are also solutions to our problems. I got 2 yeses. Can we go for 3? And that is the weird one. So let's look at a particular example. So for k equals 1, we'd have pi over 3 plus 2 pi, pi over 3 plus 2 pi, pi over 3 plus 2 pi. We need common denominators, so that's 6 pi over 3. So pi over 3 plus 6 pi over 3 is 7 pi over 3. So pi over 3 was one of our solutions, but 7 pi over 3, well, where is 7 pi over 3 on our unit circle? Let me get rid of all these arrows. Oops. So where is 7 pi over 3 on our circle? Well, 7 pi over 3 go all the way around to 2 pi, and then one more. So 7 pi over 3 is coterminal to pi over 3. So if we counted around to that angle and looked at what its intersection point is, its intersection point would be the same as the intersection point for pi over 3. So the sine of 7 pi over 3 is the same as the sine of pi over 3. They're both square root of 3 over 2. So this has to be one of our solutions. So if we were just going to list solutions out, we'd have pi over 3, we'd have 7 pi over 3. But also, if we went around again, added another 2 pi, that would be add another 6 pi over 3. That would be 13 pi over 3. Okay, 13 pi over 3 is also coterminal to pi over 3 and 7 pi over 3. So the sine of 13 pi over 3 is also the square root of 3 over 2. So that's another solution. Add another 2 pi, 19 pi over 3. That would be another solution. 25 pi over 3. Adding another 6 pi over 3 is another solution. 31 pi over 3. 37 pi over 3. Oops, over 3. How about these? Nick, does it make sense where these are coming from? Adding that 2 pi, adding that rotation over and over again. So the key is I don't want to have to write all these out because there'd be infinitely many of them. So instead of writing them out, we write out this statement that says pi over 3 as our anchor. It could be anchored with any one of these, by the way. Pi over 3 and any multiple of 2 pi you want to add. So this is a shorthand for writing this entire list out forever and ever and ever. Similarly, we'd have to do the same thing with 2 pi over 3, and we certainly could. 2 pi over 3, add a full rotation to that. We're still adding 6 pi over 3, so it would be that, and 5 pi over 3, and 11 pi over 3, and 17 pi over 3, and that forever and ever and ever. I don't want to write that forever and ever and ever, so instead, we write that. How about that? That better? It does take practice. It takes a fair amount of practice. But that's the idea. We have to give, if we go back to our sign drawing up here, we have to give not only the answer that comes from our inverse, but we have to give the one the inverse didn't know about and all the copies in other periods and other rotations all the way up and down. So when we want to write out a general solution for all infinitely many of them, this is our shorthand, and we'll call this a general solution. There are going to be other times where we'll want particular solutions within particular ranges. So if we're asked to give, let's say, give the answers that are somewhere between, say just all the ones between 0 and 2 pi, that's going to be the most common. Well, that one is between 0 and 2 pi, and that one's between 0 and 2 pi. So that might be the only answers they want. We might be asked to give all the answers between 0 and 4 pi. Okay, so that would be those two as well. So depending on what interval, if we're asked over a small interval, we just list out the answers that are in those intervals. If we're asked for a general solution, all infinitely many of them, we can't write them all out. So we write them out essentially in code. Now, if that's working a little bit, let's try adding to it a little bit. I still want to stick with sine for this example. We'll do cosine next, but I want to solve for sine of theta being equal to, and I don't want one of our standard angles. So let's say 0.65. So we'd still solve it the same way. We'd still take that sine inverse because we're trying to get rid of the sine function to isolate our theta. So we're still going to take sine inverse. So we're still going to get a principal solution from the inverse function. So I want you guys to grab your calculators and ask your calculators, what is the sine inverse? Let's do this let's do it in degrees first. Sometimes that's nice. So in degree mode, find the sine inverse of 0.65 and tell me what angle that is. Anybody want to back Nick up with that? Talking a lot with Nick today. Nick's awesome. That's great. But I know there are, what, 5 other people here who can kind of maybe help Nick back him up a little bit there. Nicholas, got the same answer? Samuel, sounds good. Okay. So that angle is, I'm going to go with 40.5 degrees. Okay, so that 40.5 degrees is going to be one of our answers. 40.5 degrees. But we also know that anything coterminal to the 40.5, so anything that is a full rotation around and landing on that same location is going to have the same sine value. So we want to add coterminals. So we're going to add those rotations. What am I going to write to add and everything coterminal? This is always fun. Somebody other than my Knicks. What are we going to write there? Nick, you probably typed that before I said anybody but the Knicks, but that's okay. Anybody want to argue with Nick about what we should write for and everything coterminal? So both Nick and Nicholas, you're saying we're going to add that k times 2 pi. Anybody else want to back that up or argue with that? Help them out with it? Dominic, I think looks good. So let me give you guys a hint. It's not k times 2 pi. I know. Excuse me. Right, Nicholas. The reason it was plus 2, the reason it was plus k times 2 pi up here was because we were in radians. So it was adding full rotations, and 2 pi is a full rotation in radians. So since this problem is in degrees, we have to add k full rotations, but a full rotation is 360 degrees when we're in degree mode. That always gets people. And reasonably so. I say, K2 pi, that's our coterminals, K2 pi. It really should be K periods. If we're in degrees, one period is 360 degrees. So that's one of our solution sets there. The principal inverse, the 40.5, and everything coterminal to that 40.5. But that's only half of our solution set. This sign is outputting a positive ratio here. We know that sine also puts out positive ratios over in quadrant 2. Sine is also positive in quadrant 2. So even though our inverse function would never be able to hand us an answer in quadrant 2, we know there is one there. So we have to go find it. And all we know about it is that this length, that y value, is the same as this length, this y value. And in both cases, that y value is 0.65. Anybody have a clever way for figuring out what this other angle is based on what we already know? I don't know, you guys started doing good with the talking, and now I made you nervous. Perfect, Dominic. This 40.5 degrees on there has to be the same, has to be symmetric to a 40.5 degree angle there. So that kind of slate blue angle has to be 180 degrees minus the 40.5 degrees. So our other angle set is whatever that subtraction is, 139.5 degrees. And everything coterminal to that. So that would be our general solution. So you can see undoing the fact that our inverse function is restrictive is going to be a little bit of a big deal. But there is kind of almost a mantra I want you to get used to. When we use an inverse function, more specifically, when we put in an inverse function into a problem to do something, when we use an inverse function, we get how many answers? Well, 2 answers. We get 2 answers. And everything coterminal. Anytime we use an inverse function to do something, our problem breaks into two answer sets with all the coterminals. Anytime we use an inverse function, we get two answers and all the coterminals. When we use an inverse function, we get two answers and all the coterminals. Every time. Okay? So, if some nice, well-meaning person comes along and says, hey, I need the solution to cosine now of theta is equal to, say, 0.437. Why not? And we want to solve that. Again, we're going to get two solutions in each rotation. So we're going to get two main solutions and then all the coterminals. How are we going to find those main solutions? Well, we're going to take the inverse. That inverse is going to give us the principal solution, and then we're going to figure out the others. So what's the cosine inverse of 0.437? Let's do this one in radians, just for the practice. So find the principal inverse in radians. And I'll give you 38 seconds to do that. Well, that's 38 seconds. I got a 1.12 radians from Nick. Let's see if that seems reasonable. We know pi over 2 is there, so pi over 2 would be 1.57-ish. So 1.1 radians is going to be about there. 1.1 radians, that's pretty steep, so that would make a comparatively short x value. That x value at 0.4 is comparatively short between 0 and 1. So I think that's a very reasonable sounding value. Anybody want to argue with that value? I mean, it seems good in scale, but I don't know. Could be wrong. I assume you guys are either all agreeing with Nick or you're afraid of him. So we'll go with the 1.12. So here's the question. I want everybody to answer this except Nick. Answer this for me. Where is the other angle going to be? What quadrant is the other angle going to be in? In the sine equation, it was in quadrant 2. Is that going to be the same here? Is it going to be somewhere else? Where is that angle going to be and why? You essentially have three choices: quadrant 2, quadrant 3, and quadrant 4. Dominic, you went with quadrant 4. Why quadrant 4? It might just be because I told you to pick a quadrant, so you picked quadrant 4. I'd respect that, but you've got more of a why. That's good too. Or anybody else want to talk about why? That is actually the almost perfect answer. That is where cosine is positive. It's technically the other place cosine is positive. We know cosine is positive in quadrants 1 and 4. this ratio here is positive for cosine. So the other angle has to absolutely be down here in quadrant 4. If this number had been negative, our principal inverse would have been in quadrant 2, and our other inverse would have been in quadrant 3. So we want to reference this angle, or we want to be able to express this angle here. We've already got the 1.12. We need the other set. What angle is this secondary inverse at? So you can either determine that angle or tell me how you would determine that angle. Make you guys talk today. It does slow us down, though. The faster you guys talk, the better. I don't think I've heard from, like, Martin. I don't think I heard from you today. Jasmine. I'm not even sure Jasmine and Martin are people. Nah, they're probably people. Probably very nice people. Samuel, you said something today, but I lost you. 2 pi minus that? I buy that. That angle's got to be this angle here. That 1.12 is going to be mirrored down here, 1.12. So if we take a full 2 pi and subtract that 1.12, so 2 pi minus 1.12, I totally buy that. It's going to be what, 5 point, you guys tell me, 5 point something, 5.16-ish. You guys help me be a little more precise than that. Okay, maybe you can't. So that or something very close to it. I'm not sure if it's a 6 or a 7 or a 5, but it should be around there somewhere. So those are our two angles in one rotation. Remember, again, anytime we use an inverse function, we get two answers. 5.163. Okay, so it does round that way. Good. So anytime we use an inverse function, we get two main answers and everything coterminal. Oops. I always like 2k pi when I write it, but it's hard to not put that in that order. We're in radians this time, so our full rotations are 2 pi's. So that's our general solution. Also, by the way, we could have instead called this angle negative 1.12 and said it's negative 1.12 and anything coterminal. That would also have worked. A lot of people don't like having negative anchors, so the 5.16 is probably nicer. You know, it's there makes both of our answers in the first rotation, so it might be nicer, but it's not, you know, more right or more wrong. Using the, for cosine, using the whole positive negative is a nice quick trick, but doesn't always lead to the nicest answers. So didn't get too far today with solving, but this is the biggest thing that's going to happen about solving. We're going to move on to solving things that look like, say, 3 cosine 5x minus pi over 7 plus 1 equals, I don't know, 8. Can't equal 8. That's too big. Equals, say, 2. And solving this, But you can probably imagine our first steps are going to be to isolate the trig function. So we're going to subtract that 1 and divide the 3. So we'd have the cosine of 5x minus pi over 7 equals 1/3. So our first job is going to be like when we solve a radical equation. First job is to isolate the radical. Here, the first job is to isolate the trig function. And then we can invert the trig function. We'll get whatever the cosine inverse of 1/3 is and anything coterminal to it. I changed the order there, but just a habit, sorry. I want to get this done quick so you guys can go. But the 5x minus pi over 7 is also equal to, like it was up here, the 2 pi minus the cosine inverse of 1/3. Whatever that cosine inverse of 1/3 is, you have calculators, you can approximate it if you want, plus anything coterminal. So we're going to break up into those two solution sets, but we still have to solve for x. So we got to add the pi over 7 to both sides and then divide both sides by the 5 to get a final answer for what x equals. So it's a little bit more involved when we have internal arguments here. But as long as we remember to break it up into those two pieces, we'll generally be okay. Because we put in an inverse function, because it's something a restriction we put into the problem, we have to compensate for it. And anytime we do that, we get two solutions and all the coterminals. That's the important thing not to forget. Questions about that before I let you go? Nice work today, Nick. I hope that's working out better and okay. We'll talk more about these on Monday, but do read the stuff. And it takes a while to sink in, take some practice. That's why it's a good thing for us to kind of like get a look at and then have a couple days to gel over and then get back together. But make sure during those couple of days over this weekend, you play with this. You kind of let it gel, let it seep in a bit, play with it a bit, kind of go back and forth. Don't worry about going on to any of the big problems. Even just like those first 1 or 2 on the homework, have it give you a couple of those over and over again, so you can kind of get the feel for this whole 2 solution thing. It takes a while to get used to. So go play with those. Have fun. Nicholas and Dominic, you guys did good today too. I appreciate that. It's really helpful. All right. Anything I can do for you guys today? Okay. Well, then I will see you guys on Monday. If anything comes up between now and then, let me know. And have a wonderful couple days.